Let's start slowly. Take a breath. Let the noise of the day fade. Set aside your to-do list, your inbox, the ticking clock on the wall, because what we're about to explore isn't just a scientific question. It's a question that reaches into philosophy, perception, physics, and even meaning, time. We live inside of it. We measure our lives with it. But do we really understand what time is? Our experience of time, the illusion of flow. To us, time feels like a river, always flowing forward. One moment slips into the next. We wake, we work, we grow older, and we carry memories of what has been, while imagining what is still to come. Time gives our lives structure. It's how we tell stories. It's how we make sense of cause and effect. But try to pause for a moment and ask yourself, where is the present? That thin slice of reality we call now seems obvious, but when you try to hold on to it, it disappears. What we call now is already gone, and the future, when it arrives, instantly becomes the past. We experience time emotionally, too. A joyful moment can pass too quickly. A period of sadness can feel like it stretches on forever. Time isn't just something we measure, it's something we feel. But is time actually flowing? Or is that just how we experience it? Time in classical physics. A steady tick. In the 1600s, Isaac Newton gave us a view of the universe that matched how we feel about time. To Newton, time was absolute. It ticked evenly, universally, no matter where you were or what you were doing. It was like a master clock, hanging in the background of the universe, unaffected by motion, mass, or energy. This idea served physics well for a while. We used it to map the movements of planets, to build machines, to plan calendars. And for most daily life, Newtonian time feels right. But as our understanding of the universe deepened, something didn't fit. Newton's time was rigid and constant. The universe's time was not. Time and relativity, flexible, relative, interwoven. Then came Albert Einstein, and with him, a revolution. Einstein showed us that time was not separate from space. It was part of a fabric, spacetime, and that fabric could bend. Massive objects like stars and planets warp this spacetime, like a heavy ball on a trampoline. And as space bends, so does time. The stronger the gravity, the slower time flows. This isn't theory, it's been measured. Clocks on satellites tick faster than those on Earth. Astronauts experience time differently depending on how fast they're moving. In some experiments, time shifts by billionths of a second, but the effect is real. Time is no longer absolute, it is relative. It depends on where you are, how fast you're moving, and how close you are to something massive. Time as a dimension. In Einstein's view, time becomes the fourth dimension. We don't just live in three dimensions of space, up, down, left, right, forward, backward. We also live in a fourth time. Think of your life as a line. Each point along the line is a moment you've experienced: birth, childhood, now later. From the outside, your timeline might look like a frozen stretch, but from the inside, you experience it one moment at a time. That's what we call now. But what if the past, present, and future all exist at once? This idea leads to a concept called the block universe. The block universe. All moments always there. In a block universe, time doesn't move. It's all already there. Imagine a loaf of bread. Each slice is a moment. Your birth, your now, your future death, they're all slices of that loaf. The universe doesn't change. The you experiencing each moment is simply passing through the loaf, one slice at a time. This may feel strange, even uncomfortable. We like to think the past is gone, the future is open, and only the present is real. But in physics, particularly in relativity, there's no reason to prefer one moment over another. They're all equally real. So if the universe isn't moving forward through time, what is? Maybe we are. Maybe consciousness is what moves. Maybe we're not riding a river. Maybe we're the river itself, carving its path through something deeper. So now we return to the question, what is time? Not just the ticking of a clock, but the force that gives the universe rhythm and shape. We've seen that it's flexible, relative, and possibly eternal, but we still haven't answered something crucial. Why does time have a direction? Why does the past feel different than the future? In the next section, we'll gently explore the arrow of time, why it flows in one direction, and how that flow might come not from space, not from physics, but from something as simple as entropy. Time is strange. We've seen that it bends, that it moves differently depending on speed, gravity, and space. But there's something even stranger, something we all take for granted. Time moves in one direction. We remember the past, we don't remember the future. A glass can fall and shatter, but shattered glass never leaps back together. You can grow older, but you cannot grow young. This is what we call the arrow of time, the sense that time flows forward, never backward. But here's the mystery. The fundamental laws of physics, the ones that govern atoms and motion and light, don't care which direction time flows. They work the same whether time moves forward or in reverse. So where does this arrow come from? Why does time have a direction? Let's begin with a concept from thermodynamics, a word you may have heard before: entropy. Entropy, the engine of irreversibility. Entropy is a way to measure disorder. Think of a clean, tidy room, everything in its place, books on shelves, clothes folded, floor swept. Now imagine tossing everything into the air. What do you get? Chaos, mess, disorder. That's an increase in entropy. And here's the key. In almost every natural process, entropy increases. Not because the universe wants disorder, but because there are more ways for things to be disordered than ordered. Take a deck of cards. There's only one way to arrange it in perfect numerical order, but trillions of ways to shuffle it into randomness. This principle shows up everywhere. Ice melting into water, a cup of hot coffee cooling down smoke, dispersing in the air, stars burning through their fuel. All of these processes move from order to disorder, from low entropy to high entropy. And that, in a sense, gives time its direction, memory, and perception. But entropy isn't just about physical objects. It affects how we remember. We remember the past because it was more ordered, and we can't remember the future because it hasn't been sorted yet. When you take a photo, you're capturing a moment of structure. You don't take photos of the randomness that comes next. In fact, some physicists believe the flow of time is entirely linked to entropy, that it isn't a fundamental force or dimension at all, but simply our way of describing the unfolding of disorder. This is a powerful idea. It suggests that the arrow of time is not built into the fabric of the universe, but into how we see it. Time might not flow. Disorder does. And we, in turn, interpret that change as movement through time. Could the arrow reverse? Now here's a thought experiment. Imagine a universe where everything suddenly reversed. All the atoms, all the particles, every motion playing backwards. From the outside, you'd see chaos becoming order. Shattered glass reassembling. Smoke collapsing into a match. Ashes forming into a fire. From inside that world, though, everything would still feel normal. People would remember what came before their new present. They would feel time flowing forward, just in a reversed environment. This shows us that the arrow of time isn't just physical, it's also experiential. It's built from memory, from causality, from the story we tell ourselves about what has come before. What about the Big Bang? So where did this arrow begin? The current theory is that the universe began in a state of extremely low entropy, high order. That was the Big Bang. From that moment, entropy has been increasing ever since. And because it started so ordered, everything that followed had direction. Time flows forward because the universe started in a rare, organized state, and it's been moving toward disorder ever since. Even the formation of stars, galaxies, and life arise from local decreases in entropy, made possible by a universe that's growing more chaotic overall. The deep mystery. So, where does this leave us? Time's arrow may not be carved into the laws of physics. It may come from probability, from statistics, from the fact that disorder is easier than order. And yet, the arrow gives us a sense of motion. It gives us memory, aging, history. It gives us change. It makes the universe a story. In the next section, we'll shift focus from entropy to something even more strange: how time behaves near gravity, black holes, and the edge of what we can see. Because time doesn't flow the same everywhere. Let's step gently into one of the most haunting, beautiful ideas in modern physics: gravitational time dilation. Imagine standing at the base of a mountain. You look up, watching clouds drift lazily over the summit. Now imagine you have a clock, and so does someone standing at the very top. You both press start at the same moment, but here's the twist. After enough time passes, your clocks will no longer agree. The clock on the summit will be ticking ever so slightly faster than the one you're holding at the bottom. Not because of faulty gears, not because of temperature or wind, but because of gravity. This isn't science fiction. It's one of the most astonishing truths revealed by Einstein's theory of general relativity. Time moves more slowly in stronger gravitational fields. Let's explore why and what it means. Spacetime and gravity. In Newton's universe, gravity was a force, an invisible tug between masses. But Einstein offered something different. He said gravity isn't a force at all, it's a curvature of space and time itself. Mass, like that of a planet or a star, bends the fabric of spacetime. And anything moving through this curved fabric, light, objects, even time itself, follows those curves. You can picture it like a soft rubber sheet. Place a heavy ball in the center, and it creates a dip. Now roll a smaller ball nearby. It curves toward the dip, not because it's pulled, but because the surface itself is sloped. Now imagine time as part of that surface too. Where the sheet curves more deeply, where gravity is strongest, time stretches out. And this isn't just a metaphor, it's measurable. Clocks in the sky. We've tested this in the real world. On Earth, gravity is slightly weaker at higher altitudes, so if you place two atomic clocks, one at sea level, one on a mountain, the clock at the higher elevation ticks faster. In fact, even the satellites that run our GPS systems experience time differently. They're far above the Earth's surface in a weaker gravitational field. To stay accurate, their clocks must correct for the faster passage of time, by billionths of a second. Without that correction, your phone's GPS would be off by kilometers every day. So we don't just believe gravity affects time, we rely on it. Black holes and the slowing of time. Now let's go to an extreme. Imagine a black hole, an object with so much mass packed into so small a space that not even light can escape its gravity. Near the black hole, space-time is stretched to a breaking point. If you hovered just above the black hole's event horizon, the point of no return, your time would crawl. From your point of view, everything seems normal. But to a distant observer, your clock would tick infinitely slowly. If you spent an hour near the event horizon, 1,000 years might pass for someone far away. This is called gravitational time dilation, and it means time can stretch and slow depending on where you are. The deeper the gravity well, the slower the passage of time. In theory, if someone could survive long enough near a black hole, they could jump into the future, their personal clock ticking slowly, while the universe ages rapidly around them. The human implication. This idea changes how we think about time. We often say we all live in the same moment. But this isn't quite true. Depending on your velocity, your location, or the gravity around you, your moment can be slightly different from someone else's. Time is not absolute, it's local. And that leads to a quietly profound realization. There is no single now that we all share. Instead, each of us carries our own thread of time. stretch slightly differently depending on where we are and how we move. It's humbling and beautiful. We are all living in the same universe, but not quite in the same time. What comes next? So far, we've seen how time flows forward because of entropy, bends and stretches in the presence of gravity. But time isn't just something that affects motion and physics. Time is also what defines the structure of the universe itself. In the next section, we'll zoom out, way out, and ask, how did time begin? What happened at the moment of the Big Bang? And could there have been something before time? Let's explore the mystery of cosmic time in the next chapter. Close your eyes for a moment. Try to imagine nothing. No stars, no galaxies, no planets, not even empty space, just nothing. And now imagine this. From that nothing, in a single immeasurably small moment, everything began. Space, matter, energy, and time. This is what we call the Big Bang. Not an explosion in space, but the sudden appearance of space and time itself. And here's the question that has fascinated cosmologists and philosophers alike. Did time begin at the Big Bang? And if so, what came before it? Let's explore this gently because the answer touches the limits of what we can understand. What was the Big Bang? About 13.8 billion years ago, the universe began from a state of extreme density and heat. All of space, all of energy, all of time itself, compressed into something smaller than a single atom. Then, in an instant, the universe expanded. It didn't explode outward into empty space. It created space as it expanded. Galaxies were not hurled through the universe. The universe stretched, carrying them with it. And here's where things get strange. Because this moment of creation, the Big Bang, was not just the birth of space and matter. It was the birth of time itself. According to our best models, there was no before the Big Bang. Not because something existed and was destroyed, but because the concept of before simply didn't exist. Without time, before has no meaning. It's like asking, what's north of the North Pole? Time begins with space-time, it turns out, is not separate from space. They are woven together in the fabric we call space-time. So when space was born, when that first spark of expansion occurred, time came into being with it. This means the question, what happened before the Big Bang, may not be answerable. There may have been no time in which to happen. And while this can feel unsettling, it's also profoundly poetic. The universe and time itself may have emerged together from a state we cannot yet describe, and maybe never will. Were there other possibilities? That said, not all scientists agree on this picture. Some theories suggest that our universe may be one cycle in a larger sequence, an eternal bouncing or rebirthing cosmos. In these models, time never truly began. It simply changes its nature through different phases. There's also the concept of a multiverse, an infinite set of bubble universes, each with their own laws, their own timelines. In that view, our universe and our time may be just one thread in a vast cosmic tapestry. But so far, these ideas are speculative. They're beautiful, intriguing, but not yet proven. The limits of imagination. When we ask what came before time, we are pushing the limits of language, logic, and perception. We are time-bound creatures. Our brains evolved to think in sequences, beginning, middle, end. We struggle to grasp timelessness. We ask questions built from the very thing we're trying to escape. But maybe that's okay. Maybe the mystery is part of the beauty. That we can look out at the stars and know that somehow this all came from a moment so small, so strange, so full of potential, that it birthed everything, not just stars, not just matter, but change, cause, memory, motion, and time itself. Where we go next? So did time have a beginning? According to our best understanding, yes. But the story doesn't stop there, because while time may have begun, it may also one day end. or stretch into eternity, or cycle, or freeze, or fade. In the next section, we'll look gently forward into the far future of time. We'll ask what happens when stars die, galaxies fade, and entropy reaches its peak. Let's explore the quiet, profound idea of the end of time. Let's imagine a long time from now, not centuries, not thousands of years, but trillions. Imagine a night sky where the stars are gone, where galaxies have dimmed, where even black holes have begun to disappear. A universe not dead, but silent. No movement, no light, no warmth, and perhaps no more time. This is the far future of the cosmos, a place where time, as we understand it, may come to an end. Let's walk slowly into that deep future. Stars will die. First stars, like everything, are temporary. Our own sun, for example, will shine for about 10 billion years in total. But some stars, especially the small, cool red dwarfs, will last trillions of years. Still, even they will eventually burn out. As fusion slows and hydrogen runs out, stars will dim and cool into white dwarfs, then black dwarfs. Cold, dark remnants drifting silently through space. No more fusion, no more light. In time, the last star will flicker out. The universe will enter what physicists call the degenerate era. An age of remnants, black dwarfs, neutron stars, and black holes. No new stars, just silence. The reign of black holes. In this dark future, black holes become the dominant structure. They will consume what little matter remains, through collisions, gravitational capture, and time. But even black holes don't last forever. According to Stephen Hawking, black holes slowly lose mass through a process called Hawking radiation, a tiny quantum effect at the event horizon. It's almost imperceptible, but over time, black holes will evaporate. The largest may take 10 to the power of 100 years. That's a 1 followed by 100 zeros. But eventually, they too will vanish. And with that, everything familiar will be gone. The heat death of the universe. This leads us to the most widely accepted vision of the end, the heat death. Not heat as in fire or warmth, but heat as in entropy, the spread of energy so evenly that nothing useful can happen. No temperature differences, no energy to power stars or motion or thought. A state of maximum entropy. The universe becomes flat, cold, and empty. Not because it collapses, but because it simply runs out of usable energy. In this future, time itself may lose meaning, because nothing will change. And if change is what defines time, then the universe will be timeless once more. Alternatives to heat death? That said, the heat death isn't the only theory. Some physicists propose a big crunch, where expansion reverses and everything collapses inward into a final singularity. Others suggest a big rip, where dark energy accelerates expansion until galaxies, stars, atoms, and even spacetime itself is torn apart. There are also theories of a cyclic universe, where time ends, only to begin again in a rebirth. We don't yet know which future is correct, but all point to the same profound idea. The story of time may have an ending. A quiet reflection. This may sound bleak, a universe with no light, no movement, no memory. But there's another way to see it. We are here now, in the brief window when stars shine, when galaxies bloom, when minds can wonder and ask questions like these. We live in the universe's springtime, a fleeting moment, when there is light and time and life. And even if the end is silent, we were part of the music. We were a thought the universe had, while it still could think. So if time had a beginning, and may someday have an end, what then is the true nature of time? Is it an illusion, a dimension, a human construction? In our final section, we'll bring everything together, science, experience, mystery, and wonder, and ask, what is time really? And what does it mean to live within it? Let's conclude our journey with a reflection on the meaning of time itself. Let's pause. not to analyze, not to calculate, but just to breathe. We've traveled far, from the familiar ticking of the clock to the bending of time near black holes, to its possible beginning and its quiet, far-off end. But now we ask something deeper, something simpler, something profoundly human. What is time, really? Time as a story. We tell at its heart, time is how we make sense of change. It lets us say, this happened, and then that happened. It lets us grow. It lets us remember. Every memory, every plan, every word we use to describe life is built on time. Time gives motion meaning. It gives music rhythm. It gives our lives direction, structure, and depth. Without time, there would be no before or after. No stories. No life as we know it. And yet, time might not be something that exists on its own. It may be the shadow cast by change, a framework we place on the world to make it understandable. Some physicists even suggest that time isn't fundamental at all. That deep down, reality may be timeless, and time may emerge, the way temperature emerges from the motion of molecules. If that's true, then time is not the container we live inside. It's the language we use to describe what we experience. Time and consciousness. There's also something profoundly personal about time. Because while clocks and equations can measure intervals, only we experience the flow. We feel time passing. We carry a sense of now. We remember the past. We imagine the future. Why? Why do we experience time in this one-way stream? Could it be that consciousness is the movement through time? That we are not passive observers of time's flow, but active participants in shaping it, turning moments into memories and experiences into meaning? The gift of the present. Here's the most beautiful truth of all. You exist now, in this moment, in this brief sliver of space-time. You are alive, thinking, listening, wondering. The universe is 13.8 billion years old. It may last for trillions more, and yet, somehow you are here, at the exact intersection of what has been and what may come. This moment, right now, is the only place where life happens, where choice exists, where presence is possible. You don't have to understand all the mysteries of time to appreciate the gift of now. A final thought. So, what is time? Maybe it's a dimension. Maybe it's entropy. Maybe it's just the way we tell the story of a changing universe. But whatever it is, you are part of it. You are made from stardust, moving through a universe of light and gravity and possibility. You are the cosmos, aware of its own unfolding. You are time, watching itself pass. So be gentle with time, with yourself, with each moment, because it's all we ever truly have. Thank you for listening, for wondering, for taking this quiet journey through something so vast and so close. Stay curious, stay present, and always stay cosmic.